let's start the next part of the course, which is retaining walls. And we'll probably, I think I've got, I'm not 5 or 6 videos on this subject and 2 slide sets. Before I get into that, let's go ahead and take care of a couple of items. One of them is one of the things that I've had to do, and I did it last semester, was to take a course which was face-to-face and move it online in a very short span of time. And many academics had this experience, so I'm not unique in that regard. However, you know, many of my students, I think, wanted more of the face-to-face type of experience. And what I have tried to do in this video series, the way I've done it, particularly with just me here and the slides there, is to have an experience which is more like what is kind of approximate what I do in class. And basically what that means for those of the naysayers in the group is that my lectures are in this format are as rambling and incoherent as the ones I gave in person. So rest assured that that is the case. The second thing is concerning resources. I have a little bit different view from my colleagues there on that subject. Many of my colleagues simply teach straight out of the book. I don't think that's as common as it used to be. When I was undergraduate, I had several courses taught that way, and I wondered, well, why did they do it this way? Why would just read the book and be done with it? Well, when I first started teaching, I tried to get away from the book, and everybody told me, well, you should stick with the book. So what then there are those who say, well, if you can't figure it out, go look it up. And there's lots of resources out there now online. Lots of them. Lots of them are more technically polished, and you'll see. But there are my warning with using online resources in this course is that in this field, it's very frequent that the methodology that I will teach you and those which are in the online resources are frequently different. And I'm taking out the whole problem of students misapplying something they see online in the course. We have that problem, but that's a different issue. That requires a little discernment on your part, and sometimes it works and sometimes it doesn't. You know, they just sort of, but many, and I used them. I did not get my PhD till 2016. I used online videos and whatnot to help me through that experience. So I know where you're coming from on it. However, my view of resources is different. I'm coming up on the 23rd anniversary of vulcanhammer.net as a website. And one of the things I wanted it to be, and it took a while for this to actually evolve. I started out with a more narrow focus and broadened it as time went by. And some of that broadening was due to my teaching experience at UTC. But my objective is to be a resource to the geotechnical industry, both the practitioners and to some degree the academics. I've stayed away, posting lots of papers. We'll fill a website up, but it won't necessarily inform people about what's really going on without doing an enormous amount of digging. I've tried to stick with monographs, most of them from the U.S. government for copyright reasons. And over the years, I've wanted to be the resource. I've wanted to be the place when people had questions and needed information about design techniques and construction techniques in geotechnical engineering, that they would come to vulcanhammer.net. And particularly in the early years of the site, by the early years I mean the 2000s, I was very successful in that. Today, there's a lot of competition out there, and I'd be the first one to admit it. But I also know that I still get a fair amount of traffic in this industry, and I still have many resources that are hard to find somewhere else. So when I set up, my courses, I kind of set those with the expectation of I furnish them with the course material, I furnish them with much of the background material that they can use for their research, particularly when we get to the design project and whatnot. And therefore, I kind of expect students to look at me first in my site before they get off on something else. And there's lots of good stuff out there. The one place where that's important is that I will sometimes, will sometimes put on my websites stuff to help you do your work and to do your homework. And some of that material is something that most of you might not suspect that I'd even try, but I do it anyway. I would strongly suggest that you look at the main course webpage for this and see what kind of resources are there, because that's where they're linked from. So my advice to you is just don't, try to slog through the slides and the videos and try to make this course. Look at your book, look at also look at some of the other stuff that I have. It will save you a lot of time and work. Okay, with that out of the way, we can proceed to retaining walls. And I put this photo of the wall in the 9th Ward breached by Katrina to underscore the importance of keeping your retaining wall vertical, either completely vertical or more or less vertical. And we'll talk about the difference of that as we go along. Retaining walls are very important. Their failures are generally catastrophic because they're generally plastic failures. Although there are some, and I mentioned this I think it was last time, the gradual failures due to settlement of the walls, a couple of videos back. This is my review of, first we're going to start with a review of lateral earth pressures. And then we'll get into different types of walls. And on paper at least, a review is not necessary for me to do another one, because the way it turned out, I had to put that part of soil mechanics online right at the end of last semester. So it's out there on YouTube as well, and I will link to it from my site. You can look at that for the more detailed treatment of lateral earth pressures. This is just going to be an overview and a review of what's going on. Okay, we're going to start with a review of the lateral earth pressures. Then you see the concrete gravity retaining walls, the MSC walls, and the sheet pile walls. As I mentioned last time, retaining walls are necessary in situations where a gradual transition either takes too much space or impractical for other reasons. Ideally, a nice smooth slope would be ideal for any change of elevation. But, frequently we don't have room for it. And frequently, in some situations, such as docks, it's just not practical. Some of them look at old pictures of old ports where they actually pull ships up, or that they would actually anchor ships off and use the lighters to get to and from the ship to the shore. That's been largely displaced by the modern docks that we have, and that's been that way for a long time. There are two types of categories. There's a number of ways of categorizing retaining walls. We're going to start with externally stabilized and internally stabilized. Externally stabilized require some kind of and they mainly look at most of the retaining walls. We're going to look with the exception of MSE wall are externally stabilized. They're stabilized by some external either supports or in some cases the weight of the wall itself or balancing earth pressures or whatever. And then there are internally stabilized walls. And MSE walls are primarily where the stabilization of the wall basically comes from the internal workings of the wall, particularly with the way that MSE strips basically make their own earth support space. Different types of retaining walls. This is from your book that break it down into the different types of walls. There's also hybrid walls in the middle. And we're only going to review 3 types. There are many different types of walls out there in use. Okay. You remember that there are 2. This is where, again, attempt to reduce confusion. We divide the way in which soil interacts with retaining walls in 2 ways. The first are different states of lateral earth pressure, and that includes the at rest, the active, and the passive. And there are ways of in-between states. Actually, when we get to sheet piling, the software you use takes those into consideration. We don't, in an elementary retaining wall design, we normally don't take it out. It's either one of the 3, and usually it's active or passive. And then there are theories of lateral pressure. In other words, we know that there are active states and passive states, but what magnitude of force or what magnitude of pressure do they have? There are different theories behind that. And it depends. And of course, Jackie was an at-rest failure. It's strictly for at-rest. For active and passive, we either have planar surfaces where the surface is assumed to be a nice plane, and that's true of Rankine and Coulomb active earth pressures, although the Rankine can be derived from more Coulomb theory as well. Non-planar log spiral is the assumption behind, you guessed it, log spiral theory. You can see the difference here between the log spiral and the planar. Those are different theories of what the failure surface looks like. All of these can be modeled in FEA, and FEA will basically give you the planar surface that it thinks it's going to fail by. Okay, let's start with the coefficient of lateral earth pressures. And this is all taken out of Verroy, and you can read it again in Verroy. But basically, the idea is very simple. We talked about with the vertical stresses. Talk about stresses where are dealt with, and let's just for a minute restrict ourselves to stresses due to the weight of the soil. Those would be either total stresses or effective stresses. Those stresses are computed vertically. You've got a column of soil, so to speak. It has different weights and different buoyancy conditions, and you have an effective stress at every different point has a different effective stress all along there. That in turn, as is the case with most solids, produces a stress laterally. The ratio of that lateral earth pressure to the vertical earth pressure is called the lateral earth pressure coefficient. In theory, and there's also the formula here where it gives you the relationship between that for a purely elastic medium, which is based upon Poisson's ratio. The reason why we kind of tend to stick with K rather than using a Poisson's ratio approach is obviously because soils are not as linear as we would like them to be, usually not at all. Neutral earth pressures are basically the pressures when there is no movement of the soil laterally for any reason. And the most common state is soils without any kind of interruption. In other words, the semi-infinite mass that we talk about so often with theory of elasticity and other things. It can be, and the normal expression of this is Jackie's equation, which is listed at the bottom of this page. And Jackie's equation is a purely empirical type of thing. It is never, I don't believe, has theoretical basis to it, but it's worked pretty well. And then it's been modified for over consolidated soils over the years. It's served us well, and it can be measured in. He talks about a Camco meter, obviously a Menard pressure meter, or a Marche dilatometer can serve the same function. You stick a probe down and you push it out. You can measure your at-rest pressures that way. Active earth pressures take place when the wall, when you've got a retaining wall and the wall moves away from the soil. And what that basically means is the soil is pushing on the wall. When you push on the wall moves away. When the wall moves away, the soil pressure drops to its active, from neutral down to active. The active pressure is the most common one we'll see. And because the job of a retaining wall is to retain earth, and as that earth is retained, the wall will try to move away from the earth and have active pressures. You will also note that at the bottom that you have Voigt gives the equation in terms of both soils with internal friction and cohesion. That's important. Originally, all lateral earth pressures were determined using purely cohesionless soils, and cohesive soils have been added later. And I discussed that extensively with in soil mechanics, where you have regions in the wall where you've got no pressure at all. The wall basically holds itself up, at least for a little while, without the help of the soil holds itself up without the help of the wall, and that sort of thing. You got the tension zone or zero pressure zone or whatever you want to call it. And cohesion also affects the action of the wall below that as well. One of the tricky things with retaining walls is that frequently, there are two things. One of them is that cohesive soils are not a good idea for backfill. And by the way, I will frequently refer to the stuff behind retaining walls as backfill. That's, again, a lot of that's based on marine applications, and so you'll just have to overlook that. But normally we prefer cohesionless soils for backfill for drainage purposes. And if you do get cohesive soils, it's usually not desirable. You need to build extra drainage into the system. And sometimes, since you're disturbing and remolding the soil after a while, it's no longer really either purely cohesionless or a partly cohesionless. It really turns into it acts like a cohesionless soil from a soil mechanics standpoint with a lower phi. Passive earth pressures are just the opposite. The wall pushes into the soil. The passive pressures are much higher. And the only place we're really going to deal with passive pressures is with sheet piling, because with sheet piling they're absolutely essential to keep the wall up. We do see passive pressures. In many cases we discount them. They're just not significant enough, and they just add to the uncertainty of our calculations. And again, you see here the inclusion of cohesion. Here we have a diagram, and we looked at it last semester, and Voigt actually has one like it, where the transition from active to at rest to passive, or to put it this way, from active to at rest to passive, is kind of a continuum. It's not a clean cut kind of thing, and as a result, this is not usually many earth pressure calculations don't even consider this. Like I said, when we get to sheet pond, the software we use actually does, because what it does is you come here and then you take a straight shot up there and then over is the way it models it. It simplifies it the way we do when we make the elastoplastic model. So that's something you should be aware of, and that diagram is important because eventually you're going to have to estimate using this particular diagram how much wall deflection you're going to have before fully active or fully passive pressure set in. Rankine, you remember this diagram in soil mechanics. It assumes more Coulomb failure conditions for the soil. It does not include wall friction effects. It can be extended to include sloping backfill. It's kind of a backhanded way we do this. Coulomb allows that because Coulomb is explicitly constructed using wedge theory and that kind of thing. And as a result, and then you just simply set the delta or the friction angle to 0 and you get Rankine. And I have, again, in my presentation last semester, we went through what the Rankine equations look like with sloping backfill, either sloping backfill up or, in the rare occasion, sloping backfill down. It's not very often that backfill slopes down up to a wall, but occasionally. With Coulomb theory, we have a different, little bit different situation. It essentially has a failure. You assume a failure wedge. You compute the weight of the wedge and how it's driving. You compute the forces of frictional forces, the frictional forces along the failure surface, and all that. And that's where we get the sloping backfill, because you can actually include sloping back. You can also the sloping wall can be included in that as well. It is very unconservative for passive pressures with high values of wall friction. The reason why it wildly overestimates the lateral earth pressures for walls such as that. And if it does that, then if your wall is counting on it to support it's too high, the wall is going to fail. The formulas you see here, which come from the Soils and Foundations manual, assume that delta is positive for both active and passive pressures. Verroy uses a different notation, and if you do use Verroy's equation, you need to make sure you understand his notation completely. One thing, anytime you adopt an active, or you see equations for Coulomb, or for that matter Rankine friction, earth pressure coefficients, you need to make sure you have a diagram like this that explains their sign convention. For example, this one uses a theta, where in other words a vertical wall will have a theta of 0 and then it increases this way or decreases going back that way. Others have a situation where you have an alpha and at 90 degrees is vertical and then it changes from there. So make sure you've got your sign conventions and all that straight. Any formulation you use, whether it's from either, for example, just Verroy and the Soils and Foundations reference manual are different, and you'll see differences elsewhere. So make sure you understand what's going on. This is a diagram that shows how you make the how they actually came up with it. You've got the driving is the weight, like in the slope stability, and then you've got all kinds of resisting forces along the wall. You've got one force that he didn't mention is your frictional wall friction and whatnot is not mentioned here, but you've got a wall friction. You've got all kinds of resisting forces, normal, tangential, and all that. And the Coulomb basically relieves you of the requirement to 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 compute all that, to go through basically a statics analysis to get to a simple lateral earthquake. So it's a big time and work saver. And if it saves time and work, it usually saves the possibility of error. Log spiral theory, the big difference is the shape of the failure surface it assumes. And there are, unfortunately with log spiral, the only way that you have available to you to solve is use a chart. And this is a chart. I explained it to you last semester. And we have active charts and passive charts. As a practical matter, what we'll probably use most often is the AASHTO combination in terms of lateral earth, where faced with Rankine tends to be the most conservative, and there are there are certain applications where Rankine is going to be what we use, which is MSE walls. For others, we will use what I call the AASHTO combination, which basically is Coulomb pressures for active and log spiral for passive. This was AASHTO's attempt to get around the issues surrounding the issues surrounding Coulomb passive pressures, which are significant. So we have that to deal with. These are the charts in your book, which are used for AASHTO. There are two charts actually. The one on this side basically assumes that you have a level backfill, and you vary the phi, the angle of the wall, and you have different results. And then once you do that, you have to use once you get this, then you have to turn around and use a reduction factor to get from this through this to there. And you've got little examples here which you can follow. Over here, this chart assumes that the wall is level, but the backfill isn't. And again, you go through that, and you go through the reduction chart, and you get the same kind of result. So that's how you use that to compute passive earth pressure coefficients in the AASHTO scheme. Typical value of wall friction. This chart comes from DM7. It is old. It's been around a long time. You see it repeated in book after book after book. It's probably as good as you're going to get. There are certain types of walls where I would use Rankine theory under any circumstances. Just as a recommendation without wall friction, those would include pultruded vinyl or aluminum sheeting. I will almost use Rankine exclusively with those. Also, MSC walls tend to prefer Rankine earth pressure coefficients. If you do use, you have some. I've got some maximum wall friction suggested for design down there in the corner. With cohesive backfills, we have the issues of the drainage. We have the issues of other problems. We kind of extend cohesive, theory for cohesion soils to cohesive soils, and you've seen the formulas we've used there. The surface loading issue is, again, this is another thing I discussed in more detail in last semester. The surface loading, basically, if you've got line loads or point loads, or in some cases strip loads, you can estimate the pressure they put on the wall. And like I said, this is a theory of elasticity exercise that we went through in soil mechanics. And again, I explained that in soil mechanics. The one thing I will note is that these equations are based on Tersagi's modification of let me back up. The person that first really applied a combination of theory and experiment to this was a man named Spangler, who taught, I believe, at the University of Iowa. And he is that's the thing he's best known for, even though somewhere around here there's his soil mechanics textbook. And Spangler's experiments pretty much put the use of theory of elasticity as the way to estimate the effects of a loading along the side against the wall. And we have, surcharges of all kinds of roadways, railways, all kinds of different things we can do with this. Varroy actually has a nice explanation of how you apply theory of elasticity to this. And the only problem, there are some important differences between the way that Varroy computes it and the way you see with the Terzaghi modification of that. Terzaghi modified it according to the theory, to the results of tests. So therefore, particularly in situations where the loads are closer to the wall, Varroy and Terzaghi diverge considerably. And so you can actually see how that, if you work it out. As an example of surface loading, we have here where we have a line load of 700 pounds per foot, and what they did is they actually took, and you should check these calculations, they actually give you some sample calculations here to show how it's done, because you have you compute the M bar value. You notice from the equation, let me back up. You notice the equation for the line load, you've got M bar values, which is basically the ratio of this length to the height. You've got, for any point along there, you've got the ratio between this and the height. So you use the end value is the ratio of z to the height here, and you use those in these formulas to get a profile. And this profile, and this particular example, shows you how to compute that profile along the wall, which is the exact way of doing it. Now, there's two things I want to note about this calculation. It's an interesting calculation. First of all, probably the actually computing this involves would probably be the province of software. Traditionally, in hand calculations, what we've done is we've gone back and we've actually computed a resultant, where basically we reduce this entire force profile down to 1/4, somewhere in here in the centroid of this, and we use that. With hand calculations, that's traditionally the way it's been done. The other thing is that line loads. You're thinking, how useful is a line load? Many times it's easier for computational purposes to say take a roadway, which is a distributed load, and just concentrate it as a line load in the middle and then use it that way. So that's another way we can simplify our calculations. We need to mention groundwater effects. I spent a lot of time in soil mechanics on this issue, and we'll spend some here as well. Groundwater has two basic effects on the lateral earth pressures. The first effect is the same effect it has with effective stresses. It reduces effective stresses due to buoyant effects. I mentioned at the beginning of this lecture that lateral earth pressures are the ratio of the vertical stresses to the horizontal stresses, and leaving out any mention of any other types of stress-inducing things at the surface, uniform surcharge and point loads, line loads, all that stuff. Leaving all that out for just a second, if we have a vertical stress profile, just effective stress profile, and you need to, by the way, any lateral earth pressure calculation you do, one of the things you must do is calculate the effective stresses, effective stress profile. And then you multiply it by K, whatever, and that K may vary or whatnot as you go down. You get the lateral pressures. So if your effective stresses go down due to existence of poor water pressure, your lateral earth pressures will do likewise. If that were all there was to it, life would be good. The problem is if you have an unbalanced hydrostatic force. In other words, if the water is on this side of the wall but not on this side of the wall, then you've got problems. You've got problems because now you've got an additional hydrostatic force, a triangle force, because under hydrostatic conditions, poor water pressure increases linearly with depth against the wall. And unbalanced hydrostatic forces have caused the failure of many retaining walls. So that must be considered if you know your situation has either on a temporary or permanent basis. There's either no or not. As for example, if your water level is up here on this side of the wall, and on the dredge side it's like that, if you've got a gap there, then you know you have an unbalanced hydrostatic force and you take it to consideration. The classic example of this, and I bring it up all the time, is tidal forces. If you have a tidal drop between high tide and low tide, then and this level is based on high tide, or even if it's just based in the middle between them, you're going to have unbalanced hydro. Say it's in the middle, for example. If it's in the middle, then you're going to be varying with a hydrostatic force that, if at high tide, say this is the level in the middle, and high tide's up here and low tide's down here. At high tide, you've got a net hydrostatic force that's pushing this way, and at low tide, you've got this gap and one pushing that way. Those must be taken into considerations. For a groundwater example, we have this one. And this is one we had last semester, and I explained this to you last semester. It's in your book. And basically, it's kind of a little bit funky in that you've got a sloped groundwater table, which normally implies, well, physics there has that there's a water flow there. But for the moment, we leave the water flow issues out, and we go with this. We go with this groundwater unbalanced. It lays out this diagram very nicely of you've got unbalanced forces. You've got the unbalanced force of the water plus the earth pressure forces, and you can see here that this force comes down and then it breaks. It doesn't slope as quickly. It doesn't increase as rapidly. But then that's more than compensated for by this. And that's how you compute it only computes the pressures. For some reason, this example does not give you a force along, an unbalanced force. It really should. External versus internal stability. External, I talked about external versus internally reinforced walls. We talk about external versus internal stability. External stability is generally geotechnical stability. Stability, whether that's due to resistance, or the soil trying to overturn the wall, trying to push the wall, or you have deep-seated stability. External stability is stability of the soil around a retaining wall and to prevent the failure thereof. Internal stability is the structural integrity. In other words, if a wall breaks at some points, or in the case of sheet pile, bends at some point. This stability, these are the two stabilities. We're going to focus mostly in this course on external stability. The only place where we're going to change that. We're going to do some structural stuff in MSC walls, and we're also going to do bending moments and sheet pile. That's about it. We're going to focus on external stability. And those external stability problems will include, you'll see this diagram over and over and over again, sliding, limiting overturning, a bearing with gravity walls, particularly bearing capacity failure. And I kind of touched on that when we were talking about bearing capacity failures. You can also have a settlement issue as well, by the way. And global stability. And basically global stability means that the soil decides, I'll show these guys who's boss. And it basically like a big slope stability. In other words, you tried to make this into a retaining wall instead of a slope, but it decided to fail along a radius or a circle space which is completely outside of the wall. Believe it or not, this type of failure still happens, even because engineers can easily ignore it, particularly that and let's just be up front. This course is not going to I'm not going to consider external stability. There are software packages which will do that, and you can also use slope stability if you know what you're doing. So there are ways of computing external stability. It's very important. I mean, it doesn't matter whether you've designed down the T, it won't overturn, it won't slide, it won't do anything. But if you've got, if the external stability goes bad, you're done. And you're done in a big way. So that's just a quick overview of walls, of basic lateral earth pressures. Next time we're going to get into concrete gravity walls. And we're going to start applying some of these to, in some ways, a very elementary type of wall, but one which is still very common. So until then, thanks for watching, and God bless.